Hey everyone, welcome back. What we're really getting into this week, and you've seen this in a video already, is the things that can essentially dim the Earth, right? So we've got incoming solar radiation. We spent the last video talking about black body radiation, how much energy we get per square meter. But there are some things that provide negative feedback, essentially cooling effects, or positive feedback, which are essentially warming effects. So what we're going to talk about in this video is one that's actually one of the most difficult aspects of climate science, and that's the effect of clouds. And this is something that's been in debate for a long time. I think there really is consensus now, but what you'll see is clouds can kind of swing both ways, if you were to put it that way. So a cloud is made out of water, right? Water droplets. And actually there's water all throughout the atmosphere. We just don't see it because it hasn't kind of aggregated to the point where it becomes visible. So the difference between a visible cloud and water vapor in the atmosphere is in a cloud that's kind of like bonded together enough that you can see it, whereas just out in the atmosphere you can't. So there's a lot of water in the atmosphere, and water, this molecule, is 2 hydrogens, 1 part oxygen. It's this kind of Mickey Mouse looking molecule. What we've seen before is when we have molecules that are polyatomic, multiple atoms in the molecule, they can absorb and remit radiation, because when that radiation hits them, generally long-wave radiation, it actually transfers to kinetic energy, right? The movement, the wigglingness, and then that wigglingness radiates heat, right? And so actually water itself is an incredibly powerful greenhouse gas, and in a bulk sense, it's actually more powerful than CO2, but CO2 is what causes the water to be in the atmosphere. So we're going to see that water is like turbocharging the effects of CO2 on its own. So when we think about clouds, hopefully you guys have started to think about some of these terms that we were talking about, right? So we've got both positive and negatives. So if we have incoming shortwave radiation, an increase in clouds actually increases the albedo of Earth, right? And again, take a quick look at a photo from space, and you see there's lots of clouds over very particular parts of the Earth. And in those cases, that cloud cover is reflecting shortwave radiation from the sun before it even gets a chance to come into the Earth. So increasing clouds increases albedo. But what we were just talking about is the notion that H2O is a powerful greenhouse gas, meaning it can absorb long-wave radiation and remit that as heat. So increase in water vapor in the atmosphere, increased heat retention. So you can see clouds can kind of do both. And hopefully we're going to be able to suss out like which of those is a stronger feedback system in a response to radiative forcing. So I wanted to quickly start with just a discussion of clouds. We're not going to go full bore into cloud types. There are lots of different types of clouds, but I wanted to talk about just a few. So here, this is the surface of the Earth again, but you can see this time I drew up to 30,000 feet, where your transatlantic airplane is flying around. So at 30,000 feet, we tend to see these wispy, thin, kind of trailing clouds. You even see them on a bright summer day, way the heck up there at 30,000 feet. And we call those cirrus clouds. So you can see, obviously, those are gonna interact, very specific way with incoming radiation. Much lower, kind of closer to the ground, really in the realm of like 1 to 5,000 feet, we generally have, I'm going to kind of lump these together because they behave similarly, although they look very different, so we categorize them different. So stratus clouds tend to be these kind of like layered clouds, like if you were in, you might see these flat low-lying clouds, these stratus clouds. And then a typical fluffy cloud, you might go out and decide if it looks like a horse or something like that. Those are cumulus clouds. There's also cumulonimbus. Yeah, again, we can really kind of get deep into cloud world here. But these are kind of end members, and they're a good place to start. So these lower clouds in the range of 1 to 5,000 feet, we're going to kind of think about these together, even though they are different types of clouds. So stratus clouds tend to be stratified, horizontal, generally fairly thin. Like maybe if you look at the Boise foothills on a morning, you might see a few stringers of clouds or something. Those would be considered stratus clouds, or flat lying. But then these kind of isolated big fluffy clouds, those are what we call cumulus clouds. And both of those in the atmosphere pretty much occupy the same area, and they cover ground to a similar degree. They can both be fairly dense and not let a lot of light through. There are lots of other types of clouds. We're just going to kind of think about cirrus clouds as high clouds, stratus and cumulus as closer to the surface, right? These stratus and cumulus clouds then being closer to the surface. Also, if you add the suffix nimbus on them, it means they're rain clouds, like cumulonimbus is a big rain cloud, but like I said, we're not necessarily going to dig into that right now. We're really just talking about the effects on radiation. So I've drawn a cumulus cloud here, or stratus cloud, and these clouds, they're bright, they're generally very dense, they're lower to the surface, like I said, in the 1,000 to 5,000 foot elevation range. When we have incoming solar radiation, these generally reflect it really well. So we've got incoming shortwave radiation, outgoing shortwave radiation. So these essentially function to increase the albedo of Earth. But, so this is a very temporary and localized situation of increased albedo. Although again, you can kind of average these things out over a region. So they generally enhance the albedo that already exists, and they generally also have an immediate cooling effect. So on a summer day, if there's lots of clouds, it's going to be physically cooler, right? Again, that doesn't take too much of a jump of understanding, knowing that it's generally cooler on a cloudy day. But the other thing that's interesting is on a cloudy night, it's generally warmer, right? And that has to do with the other side of the equation, right? That has to do with long wave radiation being trapped or kind of held and remitted by clouds. So I've tried to draw up here is some cirrus clouds, those kind of thin, wispy clouds hanging around up at around 30,000 feet, where your jet's going to be flying. And they don't tend to cover a lot. They also tend to be fairly cold, so it might be negative 20 degrees Celsius up in the range where we have those clouds. And they don't increase the albedo that much. So they do have a very small cooling effect, but it's not as significant as it was with these lower clouds, with these stratus or cumulus clouds closer to the surface. They tend to be much more dense, kind of bright white and higher reflectivity, whereas these cirrus clouds don't quite do the same amount of work for increasing Earth's albedo. So hopefully at this point you're starting to see the kind of push and pull of clouds and why climatologists have had such a difficult time establishing do clouds lead the climate in this direction, or do clouds lead the climate in that direction? And really the answer is both, but like I said, hopefully we can kind of work back the notion of which one is stronger. So here I've drawn both, our cirrus clouds up here and our cumulus cloud here. Once the Earth has energy from the sun, that energy is then converted to long-wave radiation and is working on kind of getting back into space. And so that energy will be absorbed by this water vapor. But this water vapor The water vapor is there because of increased temperature, which generally has to do with CO2. And I know that it's kind of weird circular reasoning, but the amount of water in the atmosphere is a function of temperature. So warm air can hold more moisture, cooler air holds less moisture. So you can think about the volume of water that's possible to hold in the atmosphere. If you add more water than that, it just falls out as precipitation. So there's a set volume of water that can be held in the atmosphere. That's our cloud load, if you were to think about it that way. And that cloud load can't change. It's a set number. Well, there is one way to change it, and the way to change it is to actually warm the atmosphere. And so if you have warming driven by some other force, then the volume, the load of clouds we can hold on Earth increases, and now there's more water vapor in the atmosphere. So a warming atmosphere can hold more water. That water is one of the most effective things at absorbing and remitting heat. And that's kind of what we're seeing here. So as this cloud is absorbing or trapping long-wave radiation, that goes back down to Earth, right? And that's kind of all well and good. But sometimes we don't have any clouds, right? But oftentimes we do have these high-level clouds. So even these high-level clouds, when we have long-wave radiation traveling from the Earth to these high-level cirrus clouds, they will also send that energy back. So when we start to do the balance, well, the first thing that probably enters your mind is that the clouds aren't evenly distributed across Earth, right? There are areas, because of these, global wind currents, or these rising cells of air and hot falling cells of air. You guys remember the Hadley cell, the Ferrel cell, the polar cell. Some areas are dominated by clouds, whereas others aren't. There's also Coriolis force, kind of determining where these clouds generally occur. So this effect is not distributed evenly across Earth. There are some places where the albedo effect of clouds is dominant, and they tend to be kind of cold. You could maybe think about somewhere like the Pacific Northwest, right? At least kind of more coastal, places that are generally cloudier, that there's not as much energy absorbed into the Earth. Other places, the absorption and remittance of heat as a function of long-wave radiation dominates. And so who wins, right? Who wins the fight? Is it clouds cooling the Earth? Is it clouds or water vapor warming the Earth? Well, if you look at...
Well, my camera ran out of batteries and I didn't realize it, so I lost some footage. So again, here we go. But the question we were leading up to, right, we were just getting ready to talk about, was the big question, or the big reveal, or whatever the heck you want to think about it. What do clouds do? Do they warm the climate? So we've talked about how they warm the climate. So yes, they warm the climate. But do they cool the climate? We've talked about how they increase albedo, and yes, they cool the climate. So what do they do more? Well, this was a question that people struggled with for a long time. And the first thing you probably pops into your mind is like, well, cloud cover isn't universal. And actually, again, we can look at this picture of cloud patterns and notice there are certain areas, particularly in the southern Pacific, also kind of in the northern Pacific and Atlantic, kind of mid-latitudes, we see these pretty thick bands of clouds. So those areas are clouded over pretty often. Right along the equator, right, where the Hadley cell is rising, we see a pretty kind of consistent band of clouds. To the north and south of the equator, we see cloudless areas. So the Sahara Desert, for example, doesn't have much cloud coverage. So there are these patterns. And those patterns don't change that much. But when we kind of add this all together and we look at places that have fewer clouds, places that are dominated by the recapture of long-wave radiation, it turns out that kind of presently the overall effect, the net effect of clouds are actually to cool the climate. And the negative radiative forcing of clouds on average is about negative 25 watts per square meter. So remember, you can kind of put that back into context with some of the numbers that we were talking about in the last case. 237 watts per square meter coming in. So they cool the Earth. So you can see here, this is actually an image of data collected by the CERES network of satellites, I think clouds, and the Earth's Radiant Energy Systems, or CERES, C-E-R-E-S. These little guys are a family of satellites that run around and measure cloud cover and measure, some aspects of this radiation. So overall, clouds cool the Earth, but what's even kind of further unknown and kind of further not disputed but further argued about going forward is how does that change if we have increasing forcing from carbon dioxide, right? So if we're increasing the temperature of the atmosphere and we're drawing more water into the atmosphere, does the actual area that has cloud cover change? Because that's largely determined by these cells. So if that doesn't change, but yet there's more water in the atmosphere, the radiative forces likely begin to surpass the reflective kind of albedo effect of clouds. So the general consensus is that warming, that will likely shift to clouds, providing a net warming effect. Okay, well, that should cover it for clouds and kind of the realization of how clouds are kind of in interplay in the atmosphere. The next thing we're going to talk about is aerosols, which is very closely related. All right, see you in the next video.